Thank you very much, Tori, for the nice introduction and also for the invitation to speak at this workshop. Yes, so basically I understand that many of you just came from Europe and still are jet lagged, so I decided to take it easier, so not to go much into technical things and also we'll try to wake you up with some open problems, and actually there will be a lot of open problems which I will try to propose here. And the title of my talk is Fine-Grained Complexity, and somehow this is a little bit incorrect title because there was some part of the title was lost during the communication. Actually, the title was Fine-Grained Complexity of Exact Algorithms on Graphs. But when you have a very long title, usually things become wrong. And actually, with our seminar, if you noticed, or with our program, now it's become not Fine-Grained Complexity program, but I think it's become now just fine program. Or that's how it's called. Okay, but the story of the talk, or the idea of the talk, goes to July. So I had a very strange communication with Daniel Marks. So he just, in Skype, he wrote, by the way, what about a long talk on the n⁴ business? And there was some also an entire joke, assuming you can get there before November 7. But actually, yeah. Yeah. So basically, it takes some time to me to understand what Daniel means by n⁴ business. But then, and probably the right name of this talk should be just on n⁴ business. Okay, so on n⁴ business, talk of exact algorithms on graphs. So what I will speak today, so I will first try to motivate why at all we are doing this type of research, why it's interesting, and basically one of the main motivations we try to beat brute force. So I will speak about who is this brute force and why we want to beat this brute force. And then I will speak about homomorphisms, subgraph isomorphisms, and some consequences which results for these problems have on our understanding of graph algorithms. And there will be some conclusion, and what I will try to do, there will be a lot of open questions, problems, open questions and problems. Okay, so just let's start with this motivation. So we know this famous slogan that God created man, right? And some cult made them all equal. So probably not appropriate joke here, but God also created problems, right? And p-completeness theory also made all of them equal. And of course, it's not true, because if you take any area of algorithms, so if you work in approximation algorithms, of course we know that not all problems which are NP-complete are equal, right? Some problems are good to approximate, and some problems are not so good to approximate. The same things in parameterized complexity. We know that there are some nice problems, and there are a lot of not so nice problems. And similar things going for heuristics, and actually if you take any area of algorithms, probably that will be the same story. So not all problems are equal. And the approach which I want to discuss today is probably the most naive of the approaches, like if we compare with approximation algorithms or parameterized complexity. So basically we want to see if we can improve brute force directly. So, and then the whole area of this algorithms, first people try to improve brute force, and then try to improve the algorithms, try to get better algorithms. But first of all, yes, and maybe I just also will quote, give a romantic quote of Scott Aronson, who writes about also beating brute force. We want to know how much better can we do than blindly searching for the answers to the very hard computational problems. Yes, so what is this poor brute force which we want to beat all the time, right? And so this is so brute force is also in like people call it exhaustive search, or in Russian it's called peribor. And basically this is trying all possible kind of solutions, or trying all possible options. And but if you start thinking of that, what does it mean? We try to all possible options, or well, one of the natural things. What is a brute force for NP-complete problem? So every NP-complete problem, it has a polynomial. It can be certified in polynomial time. So one of the natural assumption, what is a brute force doing? Well, we just try to go through all compact representations of the problem, and if we find the good one, we say yes. If we didn't find, we just conclude with that. So basically, that can be one of the definition what is a brute force. But then even with this type of definition, if you go to algorithms, it's become a little bit unclear. For example, if you speak about clique. So for clique, certificate a kind of natural. It's just a subset of vertices. I take subset of vertices, I check if it's a clique in polynomial time, and proceed to another subset of vertices of the graph. But for example, for Hamiltonian cycle, what will be certificate? So here I can say, well, a certificate can be a sequence of vertices, and then I will have like something like n factorial certificates, and the other certificate can be the number of ages, right, or a set of ages. I can try a subset of ages and then and check if this is a cycle on n vertices or not. Even here it's a little bit ambiguous. What is a certificate and what is a brute force? But basically I will try to avoid this philosophical question. And basically in graph algorithms, a kind of a common agreement is that we always measure complexity, at least for this type of algorithms, as the number of vertices in a graph. So this is the agreement which I will try to follow at this talk. And this area is quite old. So actually one of the first results can be a result of, now it's the classic of trial and salesman problem of 2 to the n of Held and Karp from 1962. So so in 1976, Lawler gave an algorithm for graph coloring and an even better algorithm for Trig coloring. So here n, so n is the number of vertices in a graph or the number of cities one should visit. So people were working on SAT, on independent set. And during this time, so there are appearing new and better algorithms. So there was improvements for, and this actually not probably the cut of the H results here. So there were improvements for 3SAT. For coloring, there was a breakthrough in 2006 when people managed to go, this is Andreas, Tore, and Mikko, who managed to go to 2 to the n. There was a work on triviets, on tree coloring again. There was a quite technical improvement of Bagel and Epstein for independent set, for bandwidths. And of course, another breakthrough result was the result of Andreas on Hamiltonicity, which breaking this result from 1962. So beating this result. Yes. So while the area was developing quite for a long time, I think a strong push to this area was given by Gerhard Wöllinger, who wrote a very influential survey. So this survey is from 2003, and after the survey appears, there was a lot of interest again to this type of algorithms. People start working on that, and in the survey, Gerhard classified problems in 3 types of. He tried to classify the problems into 3 different sets. So one is a type of problems is a subset problem. Basically, when we want to find, we have a universe, and we want to find a subset of elements in this universe which satisfy some property. Again, clique or a SAT are subset problems. Permutation problems, it's when we want to find a permutation of the objects, and again, Hamiltonicity is one of the characteristic problems here. And partition problems, when we have a set of elements and we want to find a partition which also satisfies specific properties. So here, example is graph coloring. And if we look at the brute force for these problems, then of course for subset problem, the brute force is taken 2 to the n time. For permutation problems, it's n factorial, and for partition problems, n to the n. But luckily enough, and what is interesting, that very often for different types of problems, like for Hamiltonian cycle, while brute force is n of order n factorial, you can go below 2 to the n. But can you go below, or you can go below n factorial? But can you go below n factorial for every permutation problem? This is somehow not clear. And for some problems you can do. The same you can say for partition problems. Well, but so far, most of the research was in this area of algorithms was concentrated on subset problems. And for this type of problems, people invented or used techniques from classical algorithms, and there are a lot of development on how to do clever branching, how to analyze algorithms. So there were very specific techniques developed for these exact algorithms, like split and count algorithm. Dynamic programming, of course, was used and to obtain faster algorithms. Local search, like the Schoening result on satisfiability. And of course, for many problems, people managed to prove that brute force is beatable. And actually, there was quite clever improvement of these results. And for some problems, like satisfiability, despite of all type of results, there's no indication that we can significantly beat a brute force. And for example, for SAT problem, people become so desperate that even now we start using hypothesis which is called strong ETH, which basically say that you cannot solve SAT with n variables faster than 2 to the n, roughly speaking. Somehow, so still there are a lot of things which are unclear even for subset problems, and there are still new techniques appearing. So I will allow myself a spoiler of Daniel's talk. So Daniel will be speaking about also a new technique how to use parameterized algorithms to design exact exponential algorithms. But that's okay. But what makes algorithms cool somehow? Right, so as a people who are doing algorithms, of course, so when we design algorithms, we are happy we invented a new algorithmic techniques. We are very happy. We solve long-standing open problems in algorithms. Again, very nice. But somehow, why I think that algorithms are cool, or what makes algorithms cool? If you remember, we had at the last workshop, we had this discussion, or the panel discussion, and then Valentin asked a very nice question. And the question was, okay, look, so we are all doing complexity here. So what happens if all computational complexities will sit in one plane, and then this plane will crash? Will this be a loss for the society? And there were different opinions on that, so somehow, yeah. But so personally, I would be very upset, and not just because there are a lot of nice people in this plane, but also because of computational complexity. I am able to prove that what I am doing is cool and what I am doing is tough. Because if I design an algorithm and I cannot improve it, still there is a very good chance that by using complexity, I would be able to say, look, no one else also can improve this algorithm. And this is so this kind of a philosophical, or this makes a very strong changes in what we are doing as algorithms theoreticians, because basically lower bounds are always cool for us. And and what really this area of exact algorithms is missing is the accompanying complexity theory, because when I do an approximation algorithms, I have a very powerful tools, and this is very easy to argue that, look, what I'm doing is tough, no one else can improve it. For exact algorithms, I have a branching algorithm. Yes, I have running time, say 1.6 to the n, and then, but is it cool or not? I really don't know, because maybe someone, in 2 years, someone will come and say, look, I have a better algorithm, runs in time 1.4 to the n, etc. Of course, people try to build the complexity theory for exact algorithms, but here things become very hard, especially if you try to do it for subset problems. So, for example, there is actually only exceptional work which is built on strong ETH lower bounds, and this is actually even very surprising that these people managed to do something there. Because if you start thinking on reductions from one NP-complete problem to another, so if you say do reductions from SAT, we almost never have a reduction where, for example, in these reductions we keep the same number of variables as, say, the number of vertices, right? And this is somehow makes it really hard to build this exact lower bounds. And for example, there are like annoying things. So for example, we know that we can solve a click in time like 1.19 to the n, but can we show that there is some constant such that we cannot solve click in running time c, this constant power n, for example? Even the simple things which we somehow do not understand. So in this talk, I want to talk not about subset problems. I want to speak about permutation problems, which are solvable by brute force in n factorial. And the most typical problem for permutation problem is Hamiltonian cycle, of course. Partition problems, where the brute force takes n to the n. And the typical problem is, so here is graph coloring. And also I will speak about problems where even stranger than permutation and partition, and where brute force takes an even large, even takes worse time. And my first example of the problem is graph homomorphism problem. So graph homomorphism problem is defined as follows. Graph homomorphism is a mapping. I have two graphs G and H, and then there is a mapping from vertex set of graph G to vertices of graph H, and basically the condition I want to keep that for every H of graph G is mapped to an H of graph H. If such a mapping exists, then I say that graph G has a homomorphism to graph H. So one of the most famous examples of graph homomorphisms, if we take a look of a homomorphism of graph G to a complete graph T, or KT on T vertices, then there is a homomorphism from G to complete graph on T vertices if and only if graph G is T colorable. Right? It's easy to see. And this is actually why this problem is so popular for graph theoreticians, because whatever, so they just like to graph coloring, and this is also natural generalization of graph coloring, because if instead of a complete graph on the right hand of on the right side of homomorphism, we take any graph H, we can define H coloring of a graph G. And there is a lot of work on graph theory. There's a whole book of Heller-Neshetrill on this topic. From computational complexity, this is also an interesting problem, because there was also quite old result of Heller-Neshetrill, which says that the problem of deciding if there's a homomorphism from graph G to graph H is in P, if and only if graph H is bipartite. And of course, unless P is not equal NP. Yeah. So in one direction, it's quite easy, right? So if graph H is bipartite, then if graph G has an odd cycle, we never can map odd cycle into bipartite graph homomorphically. And if graph G is bipartite, then we can map the whole graph into one H of graph H. But the converse direction is much less trivial. So this is a quite cute and nice paper. And actually, also, if you're interested in fine-grained kind of analysis of this type of algorithms, it's also possible to show that graph homomorphism is not cannot be solved in subexponential time, or so basically you can extend this result also not to P and NP, but also P and subexponential time solvability. And basically the way to do it, one of the ways to do it, is just to go very carefully through the proof of Heller-Neshetrill, or yeah, there can be other proofs of this result. And the other way of looking at homomorphism, and this is the way of looking at homomorphism, which was strongly advocated by Laszlo Lovaso in his last book. There's the whole chapter devoted to graph homomorphisms, and basically what he's saying that it's very convenient to look at different types of homomorphisms, and what he means by that. So basically, graph homomorphism is a different problem depending if the graph H is larger than the graph G, and this is left-hand homomorphism. And then, because, for example, if graph G is small and graph H is large, so what is a kind of typical problem can be encoded as a graph homomorphism? So, for example, if graph G is a clique and graph H is huge, then basically if there is a homomorphism from G to H, this is the same as if there is a clique of size G in graph H. So this is a kind of a clique problem. On the other hand, if the graph G is huge and the graph H is small, then it's become different problem. It's a kind of graph coloring problem. So for example, if H is a triangle, then it's a 3 coloring. So there are like two, and it looks like it's completely different problems. And seems that you need a kind of different types of approaches to solve these problems. So first of all, what is the brute force for graph homomorphism? So the brute force for graph homomorphism is just this time. So just for every vertex of graph G, what we are trying to do, we try all possible mapping into the graph H. And this is exactly the amount of mapping what we have. And then the natural question is if there is a single exponential type of algorithms. And for some classes of graphs, yes, of course, there is single exponential algorithms. For example, with the joint work with Pinar and Dieter Krach, we show that if graph H is of bounded triviets, for example, or of bounded degree, then there is a single exponential algorithm. Also, this result was extended by Magnus Wallström, who showed that if the graph H is of bounded clique widths, then also there is a single exponential algorithm for graph homomorphism. And this is a result on clique widths is quite nice because it immediately generalizes the results on graph coloring. Because graph coloring is a mapping to a clique. Clique is of bounded clique widths, so this is immediately shows. Yes. On the other hand, if we take the extreme case of graph homomorphism, graph coloring, then again, so there is a brute force for graph coloring is n to the n. But it was known from 1970s that we can do coloring much faster. So there was a result of Lawler from 1972. And then also this was recently, not so recently, improved by Bergen, Husfeld, and Kovista. Yes. So, and also if you speak about left-hand side homomorphism or about clique problem, in parameterized complexity, so there were results which explaining that for this type of homomorphisms, you cannot do it better than running time, the h to the g, basically. So up to exponential time hypothesis. But what about the right-hand homomorphism? So for graph coloring, we have single exponential algorithms. And graph homomorphism is a generalization of this type of result if there is also single exponential algorithm for this type of problem. And a word of warning here is that it was not clear a priori if there is such type of algorithms or not. And basically in 2008, so Patrick Traxler proved a very nice and cute result about D2CSP. So D2CSP is a CSP where the size of domain is D and the size of constraint is 2. So basically what he shows that for this type of D2CSP, there's no algorithm of running time D power small O of n, again up to exponential time hypothesis. And because graph homomorphism is somewhere in between of these two problems, so where it will fall, it was open for some time. And basically, I want to sketch a proof of the theorem which was proved together with Sasha Golovnev, Sasha Kulikov, and Vanya Mikhailin quite recently, that unless exponential time hypothesis fails, so homomorphism from graph G to H cannot be solved in time, number of vertices of H power small o of number of vertices of a graph G. So our reduction is from 3 coloring. So 3 coloring, of course, it's known to be incomplete, and also it's known not to have a subexponential algorithm up to ETH. But also you can always reduce this result or tighten these results by making a classical reduction from Garriott-Johnson's from graphs of arbitrary degree to degree at most 4. So 3 coloring on graphs of degree at most 4 cannot be solved in subexponential time up to ETH. And the idea is the following. So I want to reduce 3 coloring to least graph homomorphisms, and then from least graph homomorphisms, we'll go to graph homomorphisms. So least graph homomorphisms is an extension of graph homomorphisms. Basically, I also, for every vertex for vertices of the graph, I also have a list which says which vertex is allowed to map to which vertices. So it's like least graph coloring. So we know that for graph coloring there's no subexponential algorithms. This reduction I want to sketch, and also the reduction from least homomorphisms to graph homomorphisms I probably will skip. Yes. So how to go from 3 coloring to least homomorphisms of the graphs. So suppose I have an instance of a 3 coloring graph on n vertices. And I want to construct an instance of least graph homomorphisms where I select some parameter r. And then the number of vertices in the graph G prime is n over r. And then the number of vertices in the graph H prime is d power r, where d is some constant. Yes, and then first of all, why this lemma holds that if I'm able to prove this lemma that I'm not able to do least homomorphism in this time? Well, this just holds because if I have an algorithm for least homomorphism of a certain running time, if I just plug in the numbers in the running time of this algorithm, then I will obtain single sub-exponential algorithm for graph coloring. And how to prove this kind of lemma? Well, I will just give a sketch or wave my hands by proving a slightly weaker assumption. So instead of proving that the size of the graph is of d power r, I will prove it for this amount. So if I prove it for this bound, I will get a big weaker statement, but it's much easier to get. Yes. So what's happening? And the proof goes up to some specific tricks for that problem. It's kind of common proof for many problems for which we want to prove that this problem can be solved in certain time up to exponential time hypothesis. So what we are doing? So we have an input graph G, the graph which we want to color, and then we split this graph into groups of size R each. So and we just identify all vertices in each group in one vertex, but we still keep adjacency between the sets. So here is example. I had a graph. I split it into groups of size 2, and then I have a new graph which keeps adjacency relation. And so in this new graph, every vertex is a group of the original graph. And then basically what I want to do, I want to construct a graph H prime such that if when I have a homomorphism from graph G prime to H prime, so then this homomorphism will immediately give me proper 3 coloring of my original graph. This is what I want to do. Yes. So the idea is, well, for every group of vertices of graph G prime, so the mapping to H prime should correspond to 3 coloring of the vertices, but also I want to keep the colorings or all possible colorings of the neighborhoods, because graph coloring is a local problem. So if I have a coloring which is proper for every neighborhood of a vertex, then this is also globally proper coloring. So the only thing I have to be careful, to see that this coloring is proper for every neighborhood of the vertex set. So this basically means that for every vertex, I have to keep track of all possible colorings, 3 colorings of the set of vertices in the set, which is 3 power r. And also I have to keep all possible colorings of the neighborhoods. So basically this gives me the running or the size of my graph. For every vertex of the graph H prime, I have to keep a huge list of something of order r power r labels. And with this type of labels, I am able to identify so not only the coloring of the vertex, but also I want to keep all possible colorings of the neighborhood of the groups around this vertex. So the only trick which I still need here is that there can be a situation that several neighbors in a graph G prime can be mapped in the same vertex in graph H prime. So this somehow will be quite bad for me, because I will not be able to recover 3 coloring out of that. But there is a trick here, because why, and this is the trick, why we need the coloring on graphs of bounded degree. Because when we have a graph of bounded degree, when we construct our graph G prime, so we take groups of vertices and we contract these vertices into single vertices, still degree of this graph is bounded by some constant times r. Right? And even if I take the square of this graph, or it's still the degree of this square will be of order r square. Which means that if I do some kind of greedy coloring on this algorithm, I'm still able to color this graph in like r square plus 1 colors. And these colors I can use as labels in my list, and to control that no collapse in the mapping of the neighborhoods will occur. That's why I need lists. And with using this trick, it's possible to prove this lemma. Yes, so that was a little bit of hand waving, and then we still need to go from least homomorphisms to normal homomorphism, which requires some work, but this is doable. So basically what's happening is, so unless exponential time hypothesis fails, we cannot solve homomorphisms in this running time. So number of vertices of H, power small o from number of vertices of G. So the next problem, which is come next, is the problem of subgraph isomorphism. So here, what I want to do, I have two graphs, and I want to decide if one graph G is a subgraph of the graph H. And this is again, this is a kind of a generic problem. It's of course, it's Hamiltonicity is a special case of that problem. Clique is a special case of this problem. So we can define the various packing problem. For example, if I want to find the maximum number of vertices disjoint triangles in my graph, it's still a special case of subgraph isomorphism. Even more exotic problems like bandwidths of a graph. So when I want to find the optimal labeling of the vertices of the graph, which minimize dilation over every h, bandwidth is a special case of subgraph isomorphisms. When graph G is an arbitrary graph and graph H is a specific graph, which is a k power of a path. So it's a so this is quite a generic problem. And for subgraph isomorphism, again, so if we look for brute force, so brute force for subgraph isomorphism will be probably, again, something like n power n, because what we do, we just try for every vertex of a graph G, we want to see where this vertex can be mapped into graph H. And also very recently, Marek, Jakub, and Arkadiusz, they prove how this problem of subgraph isomorphism cannot be solved faster than brute force. And the idea of the proof is the following. So reduction is from graph homomorphisms to subgraph isomorphisms. Okay, suppose that we have an instance of graph homomorphism here, and suppose also that for some reason I know that I know how many, for every vertex of graph H, I know how many vertices of graph G are mapped to this vertex. I don't know in which order, and I don't know which vertices are mapped, but I only guess the number of vertices. This guess I'm allowed to do because the possible number of partitions is something like c to the n, or 2 to the n for these vertices. So this guess I'm allowed to do. Okay, but if I'm allowed to do this, what I'm doing, I construct this, the new graph. So what's happening here? So if I have a homomorphism from here to here, I construct a graph where every vertex in a graph H I replace by independent set. And the size of the independent set is exactly the number which I guessed. How many vertices will be mapped from G to H. That's it, right? Because then what's happening? I know that graph G is a subgraph of graph H prime, subject to this guess, if and only if there is a homomorphism from graph G to H prime. So basically my reduction is then I take all possible guesses, so I branch in like 2 to the n cases, it's still single exponential, and then if I'm able to solve at least in one of them subgraph isomorphism, I am able to solve graph homomorphism. If I'm able to solve graph homomorphisms, I am able to solve SAT in exponential time, which will be the end of the story. So we can conclude that unless the exponential time hypothesis fails, deciding if graph G is a subgraph of H cannot be done in time 2 to the small O of n log n, where n is the number of vertices in graph H. Well, and it appears because homomorphism and subgraph isomorphism, they are quite powerful problems, and you can also play a lot with them to prove new and new lower bounds for different problems on graphs. So for some of the problems, things go just almost for free. For example, the quadratic assignment problem is a quite popular problem in operation research and combinatorial optimization. There's even a book on quadratic assignment. So basically, the problem is I have two matrices, and then I ask to find a permutation of matrix, so matrices W and D, and I want to find a permutation in matrix D which optimizes, minimizes, or maximizes the following sum. This is a special case, it's easy to see, of subgraph isomorphism. So for example, another problem which was studied a lot in graph theory, there was a called M partition. This is the problem of Fedor, Hell, Klein, and Motvany. So the problem is the following. I have a matrix M, and this matrix tell me how should I partition the vertices of my graph. So so basically for every one, it means that there should be all edges present. For every 0, it say that there should not be edges at all, and for every star, it say I don't care. So for example, coloring will be, so I put in matrix M on diagonal, I put all zeros. So basically that should be independent sets, and all other elements should be I don't care, should be star. And also, this problem is if you take matrix M as an adjacency matrix of the graph in the homomorphism, then there's a homomorphism from one graph to another, if and only if. So there is such a partition corresponding to this matrix. So again, this matrix is this problem is again special case of graph homomorphisms. Graph minus. Graph G is a minor of graph H if we can obtain graph G from H by deleting vertices, deleting edges, or contracting edges. So here is example of a graph minor. So here are the sets which we want to contract. And basically, again, so what's happening? So the lower bound for homomorphisms and for subgraph isomorphisms, it works even for the case when graph G and graph H, they have the same number of vertices. But then graph minor is a stupid case of subgraph isomorphism, because basically if I have two graphs on the same vertex set, and I ask if one graph is a minor of another, I'm not allowed to contract edges. So the only thing I can do, I can delete edges. And in this case, it's again, I cannot solve the problem in single exponential time. So graph minor goes for free, and similar like topological graph minor, shallow graph minor, actually, so the same lower bounds hold. And actually, any kind of graph modification problem you take, where you have to delete edges and plus do something, this type of reduction shows that all these types of problems cannot be solved in single exponential time on graphs. Okay, so one of the exceptions from this kind of vault of graph modification problem, it can be a little bit artificial problem, but still people study this type of problems. So if I have two graphs and I ask if I can obtain one graph just by contracting edges from another graph. And because this type of reduction doesn't work here, and actually that's a kind of so most likely, again, this problem shouldn't be solved in single exponential time. But still, for this problem, we don't know, or I don't know what's happening for this problem. So that's an open question. So the other question is also kind of dichotomy type or characterization types of problems. So if you consider the problem, so when we play with the right-hand graph H, so we fix graph H, or we fix some classes of graphs from graph H, and then we consider all possible mapping from all graphs to this class of graphs. So then we know some single exponential types of algorithms here. For example, when graph H is a clique, then it's coloring, right? Then we know that there's a single exponential algorithm. More generally, it's easy to extend it if graph H is a perfect graph, for example, or a graph H of bounded degree, of bounded tree-width, clique-width. But it will be very interesting to have a kind of dichotomy type of result, saying it's a kind of Hell-Nash-Trill dichotomy, saying, look, for this class of graphs H, there is a single exponential time algorithm, and for this type of class of graphs H, it doesn't exist. So far, I even don't have any reasonable hypothesis for how this graph H should look like, because so far, this class is they do not seem to have anything in common, right? So graphs of perfect graphs, graphs of bounded degree, graphs of bounded clique width. Yeah, so what's happening here? Any kind of characterization, it will be just nice and cute. So here. And the other question is also like for the question about dichotomy of CSP. It's also, so far we know the running times of 2 to the n, or 2 to the n log n, roughly, right? Is there any kind of running time between them for some classes of graph H? This we also don't know, right? Even this type of result saying, look, for any class graph, for any class of graphs H, you either have single exponential or you have n to the log n. That's another question. Yes. So this type of Hell-Nash-Trill theorem is definitely missing here. So the symmetric questions can be asked for when we speak about homomorphism from the other side. So like a kind of a clique type questions. So here it's yes, and actually, well, you also it's also will be interesting to play not only for fixing G or fixing H, but fixing or two of them, or to see what's happening here. So it's kind of yeah. So the other question about fine-grained complexity here. So our proof So our lower bound for graph homomorphisms, it can be extended not just for some graphs and G and H. Actually, the way we prove it, we prove it that if you take any function H as a polynomial of the number of vertices in graph G, then you can say the same lower bound holds for graph homomorphisms. And basically, it looks like we know that homomorphism from graph G and H is solvable in this running time H power big of O of G for any values or of any dependence H of G. And basically, that's it. You cannot do anything better unless exponential time hypothesis fails. But for example, if you pick up another favorite problem, graph minus, so what's happening here? So we know by Robertson-Seymour result that if graph G is very small, then we can solve the problem in times f of G times h cubed, and I think now there are results improving h cubed to h square, and it's not clear if you can improve it to h log h, but still some polynomial of h. So that's for small g, that's what we know. And we also know that for large g, it's follow from our reduction, right? That the running time should be h of g. So what, for example, happening when g is a square root of h, for example? It looks like a huge gap on our understanding what's happening for small graphs and what's happening for large graphs. And anything in between is completely open. So, for example, how many functions characterize the complexity of this problem? Is it one function, two functions, 10, countable number of functions? Nothing is clear here. Yes, so nothing in between. Yes, so so there are more specific problems. So basically, can we decide if subgraph isomorphism, when subgraph G is of degree 3, can be done in one of these times? So why I'm asking this question? Because if graph G is of degree 2, then it's a Hamiltonicity. So we can do it in 2 to the h running time. Just add a little bit to Hamiltonicity. What's happening here? Still, we don't know anything. Yes, and the note is that if graph G is of small trivets, then subgraph isomorphism can be solved by doing some dynamic programming and inclusion-exclusion. So this is kind of doable. Yes, so the very similar question is about dichotomic characterization for subgraph isomorphism now. So what's happening for different values or for different classes of H and G? Is it possible to, where is the border of tractability, or where is the border of single exponential tractability for this type of problems? Again. Yes, now I will go, I still have like 10 minutes, right? Or, yeah. And then what I want to do somehow, I want to go through different, my favorite, well, it's very biased list of problems, but I would call it like my favorite problems on graphs. And for each of these problems, still there are a lot of questions which somehow I do not understand what's happening here. So the first problem is metric embedding. So I have two metrics, just maybe say two graph metrics, and I have and I ask if there is an embedding of one metric into another with distortion at most d. What does it mean? So I'm looking for a metric such that this is embedding is non-contracting. So for every So non-contractive means that the distance in the original graph is always at least the distances in this graph. And also distortion is at most d. That means that the distances in the new graph, they are always at most d times the distances in the original graph. Okay, so what is here? Again, so first of all, the same thing, the Trig box reduction from subgraph isomorphism, right? Because if I have two graphs, G and H, with the same number of vertices, then if there is non-contracting embedding of graph G into graph H, it's if and only if graph H is a subgraph of graph G, right? So just because I'm strongly using the property that the embedding should be non-contractive. Okay, this means that unless exponential time hypothesis fails, finding a minimum distortion embedding of graph G into n-vertex graph H cannot be done in this running time.
Sorry, what will happen to distances here?
Sorry?
What will happen to distances?
What do you mean? So distances do not contract.
You want to get like essentially minimum.
I want to find, yes, if there is any, right? Because if one graph is not subgraph of the other, you cannot have non-contracting embedding at all, right?
Yeah, but what about the distances? So what will happen to distances? Do you have weights on the edges?
No. So far there's no weights. So this is even for non. So the lower bound is for non-weighted keys. Yes. And well, if a graph, if we embed into specific type of metrics, for example, if we embed into a path, then it's possible to do it. Then it's possible to do this embedding into single exponential running time. So this is requires some work. But again, embarrassing. It's embarrassing. But we, for example, we don't know what's happening if you want to embed a graph into a cycle metric. From path to cycle, binary tree. Or maybe it will be easier to show low bounds if you want to embed a graph not into a cycle but into a grid, for example. But still, actually, nothing beyond paths is known. So the other favorite problem is a tree spanner. So I have a graph, again, say an unweighted graph, and then I'm looking for a spanning tree which preserves distances in graph G with a ratio at most t. Right? So for this problem, actually, I don't know anything better than brute force. So so the brute force is I try all possible set of edges, and then I go through all spanning trees, and for each spanning tree, I'm checking this condition. So, but anything better, I don't know. So the other favorite problem is bandwidth. So bandwidth, I have a graph, and I want to find if there is a numbering of vertices from 1 to n, which optimize dilation over edges, right? Or equivalently, we can see that we can embed not in a path, but in a power of a path. So this problem is solvable in single exponential time. So there was a result of 5 again killian. And then there was several improvements in the running time of this algorithm. But for example, if we go back to 1970s, there are people studying bandwidth was one of the most favorite problem in many areas, and people were studying, for example, the parameters which were called two bandwidths. So basically, instead of a path, I want to embed a graph on a grid. Or if you think in terms of labeling, I want to label every vertex with a pair of labels. What's happening for this variant of the problem? Is it still solvable in single exponential time? Or more generally, if we embed now our graph not into a grid, but into a d-dimensional grid. Yes, graph width. And this is a kind of a joke which was at the boot camp. So Daniel Marks, in his first talk, he was saying, or should I repeat this joke? Or yes. Maybe, okay, maybe a good joke should be repeated 4 times. So basically what's happening here, Daniel Marks was teaching trivets in his slides, and basically he said, okay, I will never define you trivets, but then the next lecture he was using this definition recursively, and also I'm just also want to use the definition of trivets here recursively. So yes, so when we speak about different types of decompositions of the graph, like bandwidth, tree-width, path-width, cut-width, rank-width, most of these problems are doable in single exponential running time. So some of them are quite pedestrian, like for cut-width or for path-width. For tree-width or for bandwidth, it requires some thinking, and for rank-width, it's also. But one of the notable exceptions in this set of problems is branch width. So what is a branch width? So what is a branch decomposition? With my graph, I want to associate a binary tree, and to the leaves of this tree, I want to associate the edges of my graph. And then if I take any cut in this tree, this cut in the tree, it corresponds to the partition of the edges on my original graph, right? And then the measure of this cut is the number of vertices which separate one set from the vertices from the other. And then I'm looking for the best type of decomposition of my graph. And here the kind of brute force algorithm is again 2 to the power but number of edges m. And just this parameter is so close to trivets, it's a kind of constant factor approximation of trivets. But still, it's kind of unclear if you can do it vertex exponential. And the other kind of strange problem is the click width problem. So I really don't know what will be the brute force algorithm for click width, probably some kind of guessing partitions, guessing permutations, and things like that. But if anyone knows any algorithm for click width or how it... Okay, or forget about click widths because we even don't know how to compute the click widths of at most 4 in a graph, right? So it's but still, it will be interesting to see what kind of algorithms can be for click widths. Another set goes from topological problems. So topological problems, what is the genus of the graph, right? So what is the genus of the graph? I have a graph, and I am asking if I can embed my graph into the surface of the minimum genus such that there's no intersections, or if I can embed my graph without intersections of edges into a surface, right? Well, there was an algorithm 2 power big O of G times n, which was announced in the paper of Kenichiko, Urabayashi, Boyen-Moher, and Bruce Reed in 2008, where they say that actually the algorithms they give also works in this running time. But somehow still this type of algorithm, even if it works, it doesn't give us 2 to the n running time, because the genus of a graph, if you embed complete graph into surface, we need something. We need a handle for every edge. So basically, it's something like n squared over 2, the genus of the complete graph. So basically, even with this type of algorithm, we still don't have a single exponential algorithm.
Sorry, what do you mean? But if it works?
I don't know, because it's still I think it's Fox conference proceedings. It's 10 pages, and I haven't seen the full proof. That's what I mean. We don't continue this, right? Oh, okay. Okay. So the other favorite problem is also a very classical problem, is a book thickness of a graph. So basically, I want to embed a graph into P pages. So what do I mean by embed? I want to embed vertices on a spin of the book. And then on every edge, on every page of the book, I embed edges such that they do not overlap. So basically, on every page, this is an autoplanar graph. So there was if I want to embed my graph into 2 pages, then this graph should be planar. And basically, you can reduce the problem to the TSP problem on planar graphs, and it's possible to solve this problem in 2 power square root of n running time. But already for p equal to 3, things become much more mysterious. And basically, so book thickness is another open question. So far the trivial algorithm would be, because the problem is even NP-complete if I give you the ordering of the vertices on the spine. So then the trivial algorithm will be, I guess, an ordering of the vertices, something like n factorial. Then I guess partitioning of the edges. Well, for fixed p, I have that the number of edges should be linear as the number of vertices. But that's still very far from single exponential, or so here we don't know anything. And the final set of vertices, again, is also a favorite set of graph coloring problems. So the most annoying question here is HColoring. So basically, HColoring is a kind of, from approximation algorithms, it's a very simple problem, right? Because it's always, I have a additive factor 1 approximation for this, right? It's either degree or a degree plus 1. But if you look for exact algorithm for these problems, so the best known algorithm for this problem I know is I construct a H graph of my graph, and then I run Björklund Husfeld-Kaivista algorithm for graph coloring on that, which gives me like 2 to the power m. So basically the only running time we know is 2 power n square, and that's it, right? So anything better for this problem? So also what's happening for list coloring or K-choosability? So basically I want to identify the minimum size of the list which I can assign to the vertices of a graph, such that for any list coloring of this graph, I would be able, for every assignment of list, I would be able to pick up the proper coloring for that. So here, yes? Yes. So here I also don't know anything for that. And also there's another line or area of research where people doing kind of radial coloring problems. So basically radial coloring problems where also coloring is not local, but it depends also on distances from. So here also a lot of interesting problems. And basically, yes, story indicates that I should stop in like a few minutes. And basically I want to conclude with this. So this is a landscape taken by the landscape of Mars. And basically, this is also what's happening now. It will be very interesting and exciting to explore what's happening with this kind of permutation and partitioning problems on graphs. So far, we're really able to indicate several kind of not mountains, but maybe hills of intractability there. But still, for almost any reasonable problem there, we still know next to nothing. And basically, I think that it's a kind of exciting program. And yeah, thank you very much.
Fedor, thank you also for taking the time to have some kind of survey as an introduction. Questions, comments, protests?
Yeah. So for the Genus problem, you only need to guess a rotation system, right?
Sorry?
The Genus problem. You only need to guess a rotation system.
Yes, this gives you something like n factorial, right? Yeah.
You had a lower bound for minor testing. Do you also for immersions?
For immersion, I think the same trick works, right? Because for immersion, we just don't delete edges, and then, so it's again it's like a subgraph isomorphism. So if you have two graphs of the same on the same vertex set, right, then it's a kind of subgraph isomorphism. It's a kind of silly reduction because what I mean by silly, because yes, we know that for this special case it's like that, but for more interesting cases, like if one graph is of size square root of n of the other graphs, we don't know anything. So somehow, no, for immersions we also thought for some, yeah.
Another comment. You could parameterize that whole setup. You know, you have n to the k and k factorial and stuff like that. Are there parameterized versions of this program in some sense? You know, it's known that you can't have an n to the k minus epsilon for k dominating set unless FDT is equal to m2. So you could kind of visit that whole Wegener.
No, that's true. The answer is no, and the reason is very simple, because even so when you start parameterize things, you go much more on an advanced level of understanding, right? And here we don't understand even simple things. Well, simple. Yes, so definitely if we manage to settle this type of questions, that will be the next step in the program. But yeah, so far it's not very, yeah.
Then let's thank the speaker again and break for coffee.